Hi everyone, my name is Ziye Tao. I just finished my undergraduate program at University of Toronto, and I'm gonna go to Harvard University for data science program. So today my presentation is about expected 10-anonymity of HyperLogLog sketches for federated queries of clinical data repositories. Okay, I will start by describing how federated network of hospitals respond to a query. Okay, so federated network of hospitals has a central party. This central party will send queries to hospitals and receive answers from hospitals. Hospitals are independent to each other. They don't share any data between each other. They only share the data with the central party. So consider the following situation. The central party sends a query like how many patients have diabetes and send this query to the hospital. There are two easiest ways for each hospital to answer this question. The first way is that the hospital will directly shares the relevant medical records with the central party, like the patient's name, patient's medical records, patient's ID, like social security number, and some other things. And the method two is that each hospital shares only aggregate with the central party. So this aggregate will be the number of patients with diabetes in our case. So maybe the first hospital will share the number 1,000, and the second hospital will share the number 500. And the central party will do some statistics and count number to estimate the number of patients with diabetes. So the problem of the first method is that it leaks patients' privacy, right? Because it contains many sensitive information like patients' medical records and ID, personal ID. And for the second method, the problem is that the accuracy is low sometimes because of the overlap of patients. So the same patient may have records in different hospitals. So this patient will be counted multiple times. So this reduces the accuracy. But I have to mention that these two methods are commonly used in reality, but here we propose a new way to do so by returning the HyperLogLog sketch. So HyperLogLog is an algorithm for estimating the cardinality. Let's see how the hospital generated the HyperLogLog sketch. Let's look at the following picture. In this picture, it shows the process of generating a HyperLogLog sketch. So the first box contains patient's ID. We can assume this ID is the social security number. So this is unique for each patient and is the same patient in different hospitals. So here A represents all patients, B represents patients with diabetes. After receiving the query, each hospital will use a public known and same hash function. And this hash function will map patient's ID to a random number between 0 and 1 and represent this number in base 2 representation. So here we got hash value of patient's ID in the second box. And after that, the hospital will divide patients into M groups. So M is number of groups, and this is decided by the central party. So in our context, we see group as buckets. So here in our example, M is 4, and usually each hospital will use the first 2 bits of the hash value to divide patients into groups, because for the first 2 bits, there are 4 possibilities, right? 0, 0, 0, 1, 1, 0, and 1, 1. And here we got 4 buckets here, A1, A2, A3, and A4. These 4 are background population buckets, and B1, B2, B3, B4 are diabetes population buckets. So we can think B1 as a subset of A1, and similarly for the rest 3 buckets. Okay, the next step is that for each bucket, the hospital will find the maximum number of 0 before the first one among all hash values in the buckets. So let's look at B1 here. B1, the first number in B1 is 11010101. We ignore the first 2 bits because that's for partition, and they are the same in the buckets. So there is no 0 before the first 1 in the first number. And for the second number, 01010010, there is 10 before the first 1 in the base 2 representation of this number. So for the HyperLogLog sketch of the first bucket, it should be 1 here in right. Okay, and for the second bucket, the maximum number of zeros before the first one is 2. So the HyperLogLog sketch of this bucket is 2. And similarly for B3 and B4. And the hospital will return the HyperLogLog sketch to the central party. And the central party will combine all sketches from different hospitals and do some statistic and compute the number of the patient with diabetes. So the expected error in the final estimate is around 1.04 over square root of n. Okay. So what's the problem of this HyperLogLog algorithm sketch? So the problem is that there is a trade-off between privacy and accuracy. We can see that when we increase the number of buckets n based on the error formula, the error will be smaller. But more buckets means each bucket contains less patient, and each patient will be more easily identified. This increases the risk of privacy leaks. So we use our solution is to use k-anonymity rule. So let's look at the definition of k-anonymity rule in our context. So k-anonymity can have any other definition in our context. We only here focus on the HyperLogLog context. So a HyperLogLog bucket with value x. So this x is the maximum number of 0 before the first one among all hash values in the HyperLogLog bucket. So this bucket is k-anonymous if at least k patients in the background population have hash value where the first one is in the position x, and we call this hash values as collisions. So let's look at an example here. So A1 is the background population, and B1 is the bucket we care about. So the x for B1 is 1 here, and there are two values in the background population which have the same number of zeros before the first one. So similarly for the B2, there are 3 collisions, and for A3 and A4, there is only 1 collisions. So if we consider 2 anonymity here, if we set k as 2, because our example is very small, so I only care about 2. So, but in practice, maybe k can be chosen as 10 or even bigger number. So if we care about 2 anonymity here, the first and second buckets B1, B2 are 2 anonymous because there are at least 2 collisions. But B3 and B4 are not 2 anonymous because there's only 1 collision here. So in our paper, our main result is that we find both theoretical formula and the practical formula to compute expected number of buckets that are not anonymous. So this number can be used to evaluate the risk of returning a HyperLogLog sketch to the central party for the user. So let's first look at the theoretical formula. So before we derive the theoretical formula, we have this mathematical setting here. So A and B are 2 sets that represent all patients. B represent patients with diabetes, and we define R as the ratio between the cardinality of B and A. So R can be understood as the prevalence rate of some disease, like if we have the query like how many patients have diabetes. Okay, so next we have a hash map sigma. Sigma maps patient's ID to a random number between 0 and 1. And now we have sigma bar here. Sigma bar is a function that to find the maximum number of 0 before the first one of this number in base 2 representation. And P is a function for partition. And we define the buckets as AI, BI, AI the buckets for background population. BI is the buckets for the population with diabetes. And HIB is the maximum number of zeros before the first one among all hash value in BI. So in short, HIB is the number in HyperLogLog sketch of the S bucket. And EI is a set of collisions in background population AI. So if the cardinality of EI is smaller than K, then we say this bucket is not k-anonymous, right? So we want to compute the expected number of buckets which are not k-anonymous, which is the expected number shown here in the last line of the slide. Okay, before we solve the problem of the full version problem, we first consider the simple version. In simple version, we don't have partition function. All we can see the number of buckets is 1. So in here we have only 2 buckets, which is the background population and the population with diabetes, B and A. And in this lemma, we can compute the probability that there is there are exactly n collisions. So here we got this probability, and we will use this probability for further computation. And before we go to the forwarding problem, we first note that the cardinality of the buckets A1, A2, A3, and AM follows a multinomial distribution. And for the single bucket AI or A1, the bucket size follows a binomial distribution. And when we have a fixed background population bucket AI, the population bucket with diabetes, this bucket size follows a hypergeometric distribution. So these are easy to be observed. So we combine these two slides, and get the main result of our paper. This theorem proposed a formula to compute the expected number of buckets which have at least one collision but less than k collision. So we observe this formula. It has double sum. So the first sum is to sum over the range of the first bucket size A1. So this range is from 1 to the population size A. And the second sum is to sum over the range of the bucket size of population with diabetes. So it's a cardinality of B1, which the range is from 1 to the minimum value of A and B. Okay, so what's the problem of this theoretic formula? This problem is the time complexity. So the time complexity of this formula is quadratic in the size of population. So even when the size is not that big, like 1,000 or 10,000, it is already impossible to use this theoretical formula to compute the expected number. So we need to reduce the time complexity by approximation. So here we have two approximations. The first one used concentration inequalities. So the idea is to apply concentration inequality on the bucket size A1, B1, because we know their distribution, and we can apply proper concentration inequality to make sure that the error is not bad. And we restrict the range of A1, B1 to a smaller interval, LA, UA, LB, UB, and keep every other things unchanged. And we got this approximation here, E1. So in our paper, we choose the interval as mean value plus and minus 5 standard deviations for the proof. And in this case, the time complexity of the approximation is linear in A over M, which is the mean value of the bucket size. So in practice, user can choose other interval and keep the error acceptable. So in this paper, we prove the error bound theoretically and empirically. So I will talk about this later. But the problem of this approximation is that one, A over M is quite big. So when population size is quite big, such as like 10 to the power of 7, and the number of buckets is quite small, like 100, this approximation is still too slow. So we need to further approximate that. So we have the second approximation, A2 here, is the mean field concentration. In this approximation, we further approximate the bucket size B1 as its mean value, R times A1. So we just get rid of the second summation and leave one summation here. So in this case, the time complexity is linear in the square root of A over M, which is much better than the first approximation. But this approximation is not always accurate as the first one, especially in the case that A over M is small. The error will be very bad. But fortunately, when A over M is quite large, its approximation is accurate, and it is the case that the first approximation that is too slow. So based on these two approximations, we have a fast and accurate formula for computing the expected number in almost all cases. So another result in our paper is that we construct this table, a trust table for user to determine which approximation method they should use. So when we construct this table, we've put the accuracy at the first level, as the first priority. And when the running time is below 10 minutes, we always choose the first approximation, which is faster, which is more accurate. And when the running time is more than 10 minutes, we go to the second approximation. And the error bound error of this approximation are all acceptable. As you mentioned here, 10 minutes are single thread time in our computer. So, and our computation are parallelizable, so the user can use other tools and to reduce the running time. Okay, so this is a trust table. And in our problem, there are three main variables here. The first one is the prevalence rate, R, and the second variable is the population size, A, and the third variable is the number of buckets. We combine almost all possibilities of these three variables to make this table for users to refer to when they, in almost all cases. Okay, now let's look at the errors of approximations. In this picture, it shows the difference between approximations and simulations. Approximations are computed based on the trust table. And in this case, we cannot use the theoretical formula to compute the real number of expected value. So I use simulations to estimate this real number, expected number. So in each simulation, I first generate a bunch of random number between 0 and 1 to represent the hash value of patient's ID. I didn't use any real medical data here. I just used the random generation function. And I followed the HyperLogLog algorithm and count the number of non-10-anonymous buckets and compare this number with our approximation. So when the number of buckets 100 and when number of patients range from 10 to the power of 4 to the 10 to the power of 7, the absolute value of errors are always below 2, which is quite good. And when number of buckets 1,000, the absolute value of error is below 3, which is also acceptable. Okay, so now let's look at another interesting computation result. So in this computation result, so when R is fixed, so the prevalence rate is fixed, a roughly fixed constant fraction of buckets are non-10-anonymous. So, and this constant is close to the probability that there's at least one collision and no more than 10 collisions when the bucket size is at mean value. So if the user are not very sensitive to errors, they can use this constant to estimate the expected number. Okay, so in summary, we developed a method to quickly compute the expected number of non-anonymous buckets in HyperLogLog sketch in almost all situations. And we control the computing time under 300 seconds. That's the single thread computation time, and in almost all cases. And we provide computation code on GitHub. So if the user need to compute this expected number, they can use this code here. Okay, so at last, let me thank Griffin and William as the co-author of this paper. Okay, that's all for my presentation. Thank you.